Well, thank you very much for the opportunity to speak here and also to host me for this period of that has been really terrific. So I would like to tell you about some very recent work that has been done in collaboration with people that are listed here. And please let me introduce them first. One, Alexander De Witt, who was here a couple of days ago, and I think he did an internship here at the École Normale during his master with Alexandros. Michel Frouchard, who is at the SPCI and is also in the audience. He was previously a postdoc at Chicago. Tali Hein, who is also in the audience as a PhD student at Chicago. And my friend and collaborator, Federico Toschi, who is an expert of turbulence and numerical aspects of that. So the title of this talk, somewhat exuberant, is Odd Turbulence. And I would like to first say what I mean by odd turbulence. In particular, the word odd, it doesn't just mean strange. It has a technical meaning that I like to highlight. And in particular, this is a story of how patterns, more precisely pattern formation, emerges from arrested turbulent cascade. And I'm going to explain the meaning of all of these terms in case there are people in the audience who are neither aficionados of pattern formation nor turbulence. I think the organizer allowed me to encourage people to interrupt with questions. So if you have some questions, comments, objections, please interrupt, and I'll do my best to clarify or to correct. So let me first say, what is the simplest picture of pattern formation that people typically learn in school? At least this is what I did learn in school. If you want to understand a pattern forming in nature, and this is a somewhat personal choice, is my cat Lauro, who sports a very delicate patterns of spots. And this type of things exist throughout biology, material science, pattern characterized by a given wavelength. The wavelength could be, for example, the spacing between these spots. And the generic question is, not only for feline science, but also for material science and physics in general, is what controls the wavelength or the inverse wavelength of these patterns. And the simplest context where this question can be posed mathematically is perhaps highlighted graphically in this plot here. Imagine that you have an homogeneous state that is initially completely structureless. Then what you can imagine doing is a decomposition in modes of this field, Fourier modes. And you can ask yourself, what is, and you assume that there is an instability in the homogeneous pattern. Some of these Fourier modes will grow. And if they grow, you can plot their growth rate as a function of wave vector, whatever is the label that you used for your modes. And there will be typically one wavelength, one wave vector, that is growing faster than the other. Okay? So in this very simplistic or simple picture of pattern formation, the mechanism of wavelength selection comes from a linear stability analysis. Now, as the mode grows, the nonlinearity in underlying equation will become important in determining the pattern. But at least in this very simplified picture, the mechanism of pattern selection or wavelength selection is a linear one. Okay? So the things that we're going to be talking today lie at the opposite extreme of this. We're going to be discussing mechanism of wavelength selection that are strongly nonlinear. And in fact, they originate from the physics of turbulent cascades that I'm going to explain for those who are not familiar with this context. So, excuse me. What is a turbulent cascade? Now, this is not a substitute for a full class on turbulence, and I understand that in the Master of Complex Systems here, there are entire courses devoted on this topic, taught by Bruno Andreotti and other friends of mine. So this is my one slide summary of it. Okay? So what is shown here is the power spectrum of a fluid. So imagine having a fluid, and you can look at the power spectrum that V is the velocity field, K is the wave vector, T is time. And the power spectrum in turbulent flows, as a function of K, exhibits this characteristic power law, okay? Investigated by many people, including most notably Kolmogorov. And I'm going to give you an intuitive explanation of this in a moment. And in order to do that, I would like to introduce Navier-Stokes equation. Many of you might have seen it before. It's the key equation that governs the motion of fluids. And I've rewritten Navier-Stokes equation. Here there is, if you like, the inertial terms. Here the gradient of pressure. Here is the Laplacian of the velocity that controls the viscosity. I've rewritten it, following, of course, a glorious tradition of many centuries, in dimensionless form. Okay? In particular, what you can imagine doing, if there is a characteristic scale of velocity, you can normalize the velocity by that scale. If there are characteristic length, you will normalize them by a characteristic length, and etc. And then you can construct this dimensionless parameter known as a Reynolds number. Okay? The beauty of doing that, I mean, of course, writing things in dimensionless form is generically useful in whenever you try to solve problems. But here, you could sort of see the immediate impact that it has on writing this equation. The left-hand side, that is responsible for inertia, is multiplied by the Reynolds number. Okay? That means that when these Reynolds numbers, for example, when the velocity scales are very large or the viscosity are small, in the sense highlighted here, when the Reynolds number is much larger than 1, the left-hand side of this equation dominates on the right-hand side, which means that in that extreme limit, things like viscosity, for example, that's on the right-hand side, can be neglected. What this is saying is that fluids, for example, at very high speed, will be dominated by processes of fragmentation and of structure, redistribution of energy, but not dissipation. Because at those length scales, large length scales, dissipation is essentially not important compared to the left-hand side of this equation. Now, this is a very simple qualitative insight, somehow bastardized in 30 seconds of explanation, but is one of the starting points of more sophisticated analysis that explain the emergence of this power law, or this for example, Kolmogorov and others studied in the following form. What happens in that regime where dissipation cannot occur is that things like large eddies or large vortices can fragment without dissipating into smaller and smaller and smaller ones. So if you view this process in K-space, you will have a flux of energy from large scale to small scale. Okay? And Kolmogorov, in a tour de force mixture of physical intuition and mathematical analysis, managed to extract, and I'm going to review it momentarily, also the power law of that, the power of that, the scaling of that power law that I reproduced here. There's one of my favorite quotes here in science by him, that there is a fine layer between the trivial and the impossible. A mathematical discovery I made in that layer. And I think that his analysis certainly deserves to be in that very thin layer. And he has done it a few times in his career. Now, if you look at this form here, this power law, even without being an expert in turbulence nor pattern formation, you may ask the following question. It seems like a rather singular premise to try to extract a length scale from a power law. And that's actually almost the opposite of a wavelength selection, right? A power law is scale invariant, and this explanation underlies that. So yes, this seems a bit unreasonable at first, but hold your horses for a couple of minutes, and I'll tell you our reasoning step by step. First, I would like to take another step and tell you that not all turbulent cascades are born equal. It depends a little bit on what type of fluid that you're looking at. And here we will get close momentarily to topics on which there's great expertise here at the École Normale, in particular Alexandros, who has written a very nice review on this. Imagine that instead of considering a fluid that is in a box and is just driven to very high Reynolds number by increasing the speed, you are also simultaneously rotating that box. Okay? So now it's a slightly different setup. And as a matter of fact, this experiment is routinely performed in the Earth. What happens in that case, or equivalently, as I shall explain momentarily, in two-dimensional fluids, there is a similar story to the direct cascade from large length to small length. But in this case, there's still a power law, but it's called an inverse cascade. So energy is flowing from small to large length. And so if you imagined, if you did a simulation of for example, a turbulent flow using Navier-Stokes equation in the presence of rotation or in two dimension, you would see, and this has been done routinely here many times, you will see that the energy flux will lead, with periodic boundary condition, to the formation of two giant vortices with opposite chirality at length scales that are characteristic of the size of the box. Why is that? Because, again, in this picture, there's nothing other than the energy scale where, the length scale where the energy is dissipated, because if you go back to the formula, the Reynolds number picture of the Navier-Stokes, the Reynolds number is effectively decreasing as the length scale is decreasing. And the other one is the length of the system, nothing else. Why? Because this is still a power law. The only thing I've done is to flip the arrow of the flux of energy in these two cases. Okay? And please, bear with me. I'm presenting some of these things as fact. I'm going to rationalize momentarily. Now, the things that we are imagining, and we will start with a theoretical imagination, if you allow me, is a situation in which instead of having a direct or a mixed cascade, a direct or an inverse cascade, you have a mixed cascade. So a coexistence of both of these things. Since we have a lot of imagination, how do we imagine that looking? Well, it would be something like this. It would be a direct cascade until an intermediate wave vector, where the direct cascade a la Kolmogorov is arrested, and below it, there would be an inverse cascade that is with an arrow for the flux pointing up. And so with the arrows arranged like this, there would be an influx of energy at this characteristic wave vector, or inverse wavelength. And then, potentially at least, you could imagine inducing a pattern with characteristic inverse wavelength given by Kc, and potentially could look like a bunch of vortices separated by that length. Okay? So if one could realize this idea, if one could convince reality to do something like this, you would have a mechanism of pattern formation that is essentially triggered by the arrest of two cascades simultaneously. Okay? And now, the other way around, there will not be a flux of the energy at the structure where you want where you want the formation. And what you're saying does happen, as a matter of fact, in rotating turbulence. But we want to arrange it with this flux, and that is something that I'll have to explain how to do it. So I hope you don't mind if I've arranged this talk in such a way in which the general idea in its sort of in its sort of abstract form has been exposed before introducing potential physical system where this could be realized. Now I would like to tell you, how do you do this in nature, even notionally, potentially?
What happened to the energy flux?
Yes, so at the energy flux, we'll have to discuss it a bit more detail later, will depend also a little bit on the energy injection, whether the energy injection happens at high K or low K. But what will happen here is that we imagine that there will be an arrest. So there will be, when you inject it, I prefer to go back to this later in detail, but when you are injecting a small k, there will be still a flow down where the energy will be ultimately dissipated, but it will be partially arrested by the inverse cascade.
That's not uniform.
Yeah, no, absolutely not. Good. So how do we do this? And in order to realize this idea, I would like to introduce a solution that nature has found to this problem, or to realize is precisely what highlighted in that slide. And there's a notion called odd viscosity. And in parallel, I would like to take these two books, the theory of elasticity and the theory of what is it called, fluid mechanics by Landau-Lifshitz, and I would like to remove a couple of assumptions that are routinely done in the standard treatments. And in parallel, I would like to do half of these blackboards on fluids, and the other half of this blackboard on elasticity theory. So overall, this blackboard will cover continuum mechanics in various modifications. And I would like to also speak, if possible, to people that are in the audience who do things like high energy, for example. These two cases will be viewed as a paradigmatic example of field theories where parity is violated. Okay? So I would like to start with something concrete with like fluids and elasticity, but please take them as an example of a broader range of theories to be considered. So what is odd viscosity? Again, let me start by saying what is normal viscosity. So the simplest type of fluid again, the one that I studied from those books, is usually described as a relationship between stress and strain rate, where this V denotes velocity in the k direction and gradient in the L direction. This is called the stress. The divergence of the stress in continuum mechanics generates forces. And this object here is called the viscosity tensor. It has 4 indices to match the structure. Okay? And if in parallel to this you were doing solid mechanics, you would be writing an equation which is very similar, that relates the stress to the strain, where u is the displacement in the k direction and L is its derivative. And in between, they would have another coefficient called stiffness tensor, Kij, Kl. All right? So this equation, if you've never seen solid mechanics, is like F equal Kx on steroid, where on steroid means the continuum field theoretical counterpart of that. It's a linear relation between stress and strain. Okay? Now, in this case, and I'm going to be jumping between the two to emphasize the mathematical structure and then concentrate on the viscosity, because it's more common to study turbulence in the context of fluids than in solid, although it's not impossible to do the opposite. Usually viscosity, in the mind of most people, is associated with dissipation, meaning you would construct naturally a quadratic form involving the strain rate that tells you how much power is dissipated in your medium. Okay. Similarly, often discussion of continuum mechanics start with a notion of an elastic energy. An elastic energy that, once again, is a quadratic form of the strain. Okay? Please let me focus momentarily on mechanics. What is very common to do is to assume that the stress comes from a variation of the energy. So you're now endowing your theory with a variational structure. You're making a theory of a medium that is conservative. You're imagining that the microscopic forces in this solid have a curl of F that is different from 0. They can be derived from is equal to 0. They can be derived from a potential. So mathematically, you're assuming that sigma ij obeys this type of relationship. Huh? If this is true, well, look, this is quadratic in U. You got to derive this. I mean, that doesn't surprise anybody. But an aspect that is not emphasized enough, in my opinion, I mean, in Landau-Lifshitz is left as an easy exercise to prove, is, as many things are, is that if you demand the stress to come from a variation of a potential, there is a symmetry that is that this model must acquire. And that symmetry is the following. It's the major symmetries of the stiffness tensor. That means that if you flip these two pair of indices, that object must be symmetric. Now, I promised I'll stop talking about rank 4 tensor in a moment. A friend of mine says that I'm the only person who gets excited talking about rank 4 tensor. And the reason is that they are an embedment of symmetries. And symmetry reasoning, in my opinion, goes beyond important algebraic details. And please notice that if you replace a pair of these indices with a global index, this tells you that this matrix must be even under exchange of those indices. Okay? Now, one thing that you could say is, well, all right, I understand that if you have a closed system, you will want the system to be conservative. But what if you're trying to understand the pattern that forms in an out-of-equilibrium process, or a crystal made of biological components that have internal motors in it? You have no need to impose this, but you still can have a linear relation between stress and strain, because this is like Hooke's law. And Hooke's law is not a statement about energy. It's a statement about linearity. And the only thing you have to do at change from Landau-Lifshitz, as is known, is to say, OK, take this stiffness tensor Kij, Kl, and decompose it like any tensor in an even or symmetric part plus an odd or antisymmetric part. This decomposition is always possible. The odd part will have the following property. Oh, Kij, Kl odd equal minus KKL ij odd. Okay? Landau-Lipschitz says this not allowed. Why? Because it's talking about a closed system. What we're saying, we want to talk about active, or system where energy is pumped and taken out. So we're going to allow this as an effective field theoretical description of those systems. But that has consequences, and those consequences are very tangible, because these objects contain all the moduli that a medium can have. So if you say that now you have just another matrix that is allowed, you're going to double the normal amount of moduli that are characterizing the response of those systems, and you can classify them. Now, in the same way as you can do it with elasticity, you can do it with viscosity. Okay? You can say, and I'm going to show you physical experimental systems that do this, and understand also the microscopic origin of this phenomenon later. But just by analogy, you can say, well, look, I'm not going to, you see here, in order to have this, you are demanding that Kijkl is a variation, is two derivative of the energy. Okay? Here you're going to say, I'm going to assume that eta ijkl, actually, if you read the Landau-Lipschitz, for a simple fluid, because of similar reasoning to the one I just exposed before, you demand that this object is symmetric under this pair of indices. Okay? That assumes that viscosity is associated with dissipation. Okay? It assumes in particular that Nijkl is equal to two derivatives of the dissipation or entropy production rate with respect to the gradient of the and then by construction it has to be symmetric. However, in fluids that are characterized by internal sources of energy and even just external magnetic field or rotation, fluids that violate parity in particular, as I'm going to show you, this does not have to be the case. So the viscosity tensor can pick up a component that is called odd, or in the context of plasma physics also gyro viscosity, that has this property. Okay? If you look at this thing here, you can see why it's weird. In the same way as this object called odd elasticity is weird because it's an elasticity that does not enter the elastic energy. It affects the dynamics, but does not have a potential structure. This guy is weird because an antisymmetric object, if you put in the power here, you have an antisymmetric tensor, multiply the symmetric thing. So this does not contribute to dissipation. It's a viscosity that does not dissipate. But it will enter the stress relationship. So it will enter the equation of motion. What does that mean? Let me write down one final equation. If you have the stress, to go from the stress to the equation of motion, you say you write Newton's law, rho times acceleration equal, and here you write, now I indicates, as usual, the component. You take the derivative of the divergence of a stress. This assumes linear momentum conservations. And this is your ma equal f. Now, if this sigma ij has a component that comes from here, which has an odd viscosity in it, then that will change the equation of motion. And in fact, I can just do an exercise of plugging the simplest form of tensor that has an odd component or antisymmetric component and write a modification of Navier-Stokes that accounts for it. And I'm going to do that now. And the equation, please notice this capital D is a convective derivative. It has both partial derivative of V and the nonlinear piece that is responsible for the existence of turbulence. And then here you have the usual stuff. Gradient of pressure. I hope I get it right, because otherwise it's embarrassing if you give talks about fluids and don't know Navier-Stokes. But and then the piece, the new piece, is the one that I'm gonna write now. Please notice. I'm gonna make these comments more transparent physically in a moment, but let me introduce them mathematically first. If you write I and J as a single index alpha and KL as a single beta, saying that this object is antisymmetric under exchange means at least in 2 dimension, that you're going to be using matrices of these forms. Okay? So those are matrices associated with rotations. And this matrix, since I put a -1 here and not here, instead of I can put a -1 here and a plus or vice versa, that is a choice of parity. Okay? And you'll see, physically, that will be manifested in the physical generation of this effect by magnetic fields or rotations. So when I have this term in here, I'm going to pick up a term that is going to depend on an axis, say the axis along which the magnetic field is oriented, EZ. This is a, how do you call it, a vector of unit, maybe put the hat like that. And then in front, there's going to be a new coefficient. So let's say that if this fluid is incompressible, this is a shear viscosity. This is going to be an odd viscous coefficient. And this term, if I just literally plug it in there, is going to have the following form. Still Laplacian, like a normal viscosity, or the velocity field, but here there's a curl. Can you see what I've done? So this, if you like, it's a modification of Navier-Stokes equation that account for the presence of parity-violating viscosities. Now, these beasts occur in many physical contexts because they are, please. Unfortunately, yes. The comment here is, I violated many things. I also violated, it's a little bit easier if you're in 2 dimension. Why? Because in 2 dimension, you can have a vector that tells you how you're going to be chiral, like a magnetic field that points out. And then in the plane, you can be, you can be isotropic, for example, right? And in 3 dimension, unfortunately, this vector's got to go somewhere. So that's a price you have to pay. And one little thing that I've done that I cheated it a bit is that notice that this object has, say, 3 dimension, 3 times 3 times 3 times 3, must be large, 81 probably. And here I boiled it down only to 2 numbers. So I gave myself freedom to simplifying the model. A full group theoretic characterization of these things is a recent JFM paper written by Tali that you can look if you want. But this is the simplest materialization of that principle. And we're going to be working in 3D in this talk. Okay? In 2D, the odd viscosity can be absorbed in the pressure. So it does not modify bulk flow. But in 3D, this is not the case. Okay? So now that you have this, you can imagine doing many things. You could solve literally, you pick up this book, you solve whatever fluid dynamics problem you want. Like you have a ball, you have flow past a ball, how is the fluid going to behave around it? And we're doing that, and you build a lot of intuition. For the purpose of this talk, what I want to do is I want to study fully developed turbulence in this model. And in particular, notice that here there's a dimensionless parameter, the ratio between the odd viscosity and the normal viscosity. What happens if I crank up this number? Okay? Now, please notice that like any other problem in hydrodynamics, given this equation, you can calculate the spectrum. And there will be a spectrum of waves that will be characteristic of that. And same thing, you can do it also for elasticity. In this talk, I will focus on, if you guys allow me, on fluids, just to, to make it a little bit more self-contained. Please. Who? Yes, so this is the Laplacian, if you prefer like this. Laplacian. This is a vector. This thing is the normal Laplacian, the normal viscosity term. The only modification is that there is a very good point. If I understand the question is, this guy has 2 derivatives. Why does he have 2 derivatives? It has 2 derivatives because the stress has 1 derivative. And then if you're imposing the divergence of a stress, you got to have 2 derivatives. So then let me rephrase your question. Under what condition can I have 1 derivative? What symmetry do I have to break, or conservation law? The answer is linear momentum conservations. If these things are on a substrate, then I don't have to have, you see, like this equation is a simple conservation law in which the conserved quantity is linear momentum. if you assume that in addition to these things, there's also an interaction with a substrate, or your particle are self-propelled, then you can have terms that are forces that do not come from a divergence of a stress. Another thing that you could do, for sure, you could do Coriolis forces, for example. And in fact, that is a wonderful introduction. I'm just going to jot it down. Please take a look at this term and compare it with standard Coriolis. So now you're comparing a fluid without viscosity to a simple fluid in which you rotate the bucket. Then what you're going to have is not a modification of the viscosity tensor. You're going to have a body force. And the body force is, let's say that the Coriolis, the rotation in the z direction. Then you have omega naught, that is the speed at which you rotate the bucket, z, and then what is this? A cross of v. Here you don't even have derivatives. Okay? So these are all possible. Please compare the two forms. They're very similar, except that here there's two derivatives. So this is the odd viscosity. Already we can start having a preview. Is a wave vector dependent rotation. Because if I take a Fourier transform here, I pick up a factor of k squared. Okay? Here you can start to imagine how this is going to mess around with the Kolmogorov scaling. But let's do that one step at a time. I think I owe you, after this irresistible time at the blackboard, an explanation. Well, first of all, if you want to read this thing explained at a speed that is more reasonable, there is this review paper that we wrote. This is the same equation that I wrote here, but I wrote it in matrix form. Please notice how nice it is, how apparent here is that antisymmetric component. Okay? And this mu is the shear viscosity. Now, what I want to show you on this next slide is how do experimentalists do this? And where did they measure them? Please.
Just a follow-up question.
Yeah.
You have a specific axis which is z. By degree must be equal by an external factor. But this can change with space. And if this direction z depends on space,
Of course.
you get that.
Yeah, and it does. It can. But in here, I'm going to assume something particularly simple, that this z is fixed. And I'm going to tell you exactly how that cannot be the case momentarily. And in fact, generically will not be the case. So please hold your horses for one moment. So what I have here is a bunch of examples. And I want to just show you the examples. The first one where this odd viscosity. So first of all, this thing has various names. Plasma physicists call it gyro viscosity. Quantum folks interested in a quantum Hall effect call it Hall viscosity. And we call it odd because it seems like appropriate mathematically. Same concept at the level of the hydrodynamic equation. Huh? So how do you measure it in nature? Well, with electrons, people have measured in graphene. This is under a GAIM group. One example that I particularly like are these two here. So here they're spinning colloids. This is a lab done in the laboratory of William Irwin at the University of Chicago. So what William did is that he took colloids. Colloids are particles that are maybe like a micron in size. They live in water. And they can have an in-plane magnetic moment. So this guy's measured in two dimensions. And then what William does is that he puts a rotating magnetic field in the plane. By rotating the magnetic field, he spins all the particles. Okay? And then these particles interact with each other, and they form a fluid or solids. Another example done in the laboratory of Nikta Fakhri at MIT is that Nikta takes spinning embryos, following a long tradition in biophysics, and these guys spin by themselves because they have intricate biophysical motors in it, and they can make fluid or solids of the spinning particles. Okay? And one of the things that I want to show you is why is it that spinning particles in water can cause this type of effects? Well, if you take even the simplest explanation, model of what a spinning particle does in water, is that in addition to the longitudinal forces, spring-like, between the two particles, that are, central forces, because this guy is spinning, he moves the fluid around, and that will act a bit like a lubricated frictional force. Okay? Now, lubricated frictional force means that in addition to those longitudinal forces, there's going to be also transverse one called the lubrication forces. And if you pick up a fluid dynamics book, there is even formulas for this. The point for us is that the curl of those red forces is different from 0. And in particular, one of the things that you can do, Michel and myself and others have done this game, is to understand it from kinetic theory. Imagine a head-on collision between two such particles. That collision will violate parity, meaning that even if the two balls, even if the two particles, hit each other head-on, they will recoil at an angle. Now, you can do in kinetic theory a direct relationship between this non-vanishing recoil angle and the magnitude of this viscosity coefficient. And with a little bit more work that my student Egg Aaron in the audience is doing, you can also track it down to microscopic parameter with a lot more work. You can track it down to microscopic parameter of the interaction of these particles. Okay? So this is how microscopically this arises. And people have been studying it in many contexts. My favorite, back from 1970, I think took me a while to learn about this paper. It's a shame because this was done at Leiden University where I was a professor, although it was done in the 70s. I was a professor only recently. But this is work in polyatomic gases with magnetic fields. And people studied the hydrodynamics of these fluids, where presumably they're also interested in quantum effects, or at least semi-classical one. And they measured some of this coefficient about viscosity. So odd viscosity, whole viscosity, it's a real thing. However, to the best of my knowledge, has not been discussed at high Reynolds number. Okay? And what I want to show you now, in the remainder of the talk, is what happens when these effects that do exist in nature conspire with the intricate physics of turbulence that stems from the fact that in this convective derivative, there are nonlinear terms. Okay? So, I think all the building blocks at an intuitive level are on this blackboard. Okay? So first of all, let's recap what, and of course, this is, if you have questions, especially the difficult ones, you have the world expert in the audience, Alexandros, Luca Biferale, and him wrote this physics report that review all physics of turbulent cascade with a special emphasis also in their research paper on rotating turbulence. And I believe that this picture is stolen from some of their simulations. Now, this is a rotating fluid. What does that mean? Navier-Stokes, but instead of having this term, you put Coriolis. Okay? So here you are rotating the bucket. What I want to understand, by comparing this equation with this equation, is the difference between rotating the bucket with a simple fluid in it versus keeping the bucket as it is, but spinning the particle at a macroscopic level. Even intuitively, you can see that in one case, you're driving a large scale. In the other case, you're driving a small scale. Since you're driving a small scale, that effect should be enhanced at large K. And this is what the equation is telling you. Not surprisingly, because it's been derived correctly and reflecting this intuition. Okay? Now, so in the rotating turbulence, we have the inverse cascade, as I was mentioning. The odd viscosity, it's a wave number dependent Coriolis force. You see, if you Fourier transform this Laplacian, you pick up a minus k squared, right? But then after that, the algebraic structure is still the same in terms of cross products. Okay? That's what I mean, is that this is almost having omega naught dependent on k, which means that already you can make some inferences. The first thing I want to tell you is, why is it that when you have, because I claimed it, but I didn't say anything about it in terms of justification, why is it that when you have either rotation of this beast, there is a tendency to produce inverse cascades that are similar to two-dimensional modular turbulence? And the reason is that you can just look at this picture courtesy of the simulation of Alexandros, and you can actually see that the net effect of rotation is to almost straighten up the vortices in the direction of rotation. But that's not an explanation. That's just looking at the pictures. The explanation comes, at least a low Reynolds number, intuitively, from an argument called Taylor-Proudman argument. So this argument, due to these two gentlemen, goes as follows. And I'm going to explain it to you in the context of this, but it's the same mathematics. You assume, somewhat unsafely, in my opinion, that in this equation, you can establish a balance only between two terms. If you like, the one due to the odd viscosity and the gradient of pressure. You can do the same thing also for the rotation. Then, if you take the curl of both sides of this equation, the curl of grad is 0, you assume incompressibility, which is divergence of V equals 0, and you obtain this formula that tells you that gradients in the z direction of the velocity fields are suppressed. This is the indication of quasi-two-dimensionalization. Okay? Now, I'm going to give you a better explanation momentarily, or a bit more mathematical one. But the thing to already see intuitively is that the fact that the odd viscosity is a wave vector dependent Coriolis force tells you that to 0 order you can guess the answer to the question that I posed on the first slide, and why this is the right this is the right ingredient you need. Because at large, a small k, which means k magnitude of the wave vector, a small k, this is negligible, this term. So then this is gone, and you have the normal Navier-Stokes equation. This beast produced Kolmogorov turbulent, Kolmogorov cascade. And that is what you see here. Small k, 3D direct cascade a la Kolmogorov. A very high case, this object is behaving like a rotation. And what does a rotation do? It does the inverse cascade. So having this beast that is a wave vector dependent rotation allows you to interpolate from Kolmogorov to physics similar, or the inverse cascade similar to rotating turbulence. And where do they meet in between? Well, guess where? When this term and the other terms become comparable, which is where these two viscosity are roughly of the same order. Okay, I'm going to elaborate on that momentarily, please.
You rotate, so you are having two-dimensional, and then there's already inverse cascade.
But remember, what I'm doing is that when I have odd viscosity, I'm not rotating the box. I'm only considering a fluid or particle that spin at the microscope, self-spinning particles. I'm not doing in addition to that a rotation. I'm comparing the two. And I'm trying to argue that spinning the particle at the microscopic level is similar to spinning the box, to rotating the box and leaving the particle alone, but with a signature that exists in the k dependence in the hydrodynamic equation.
Should I cross off the two-dimensionalization?
Not here. No, look, looks good to me. I mean, you can do it if it makes you happy. But I mean, like what I'm just saying is that in so in 2D there is an inverse cascade throughout the spectrum. If you have rotating turbulence, there's an inverse cascade to but what I'm saying is that in odd turbulence, because maybe this is the part of the title that bothers you, there is still a two-dimensionalization, but it's not everywhere in the spectrum. It's only effectively acting in a regional k-space. Actually, now that you make me think, this is a weird idea, because what we're saying is that the dimensionality of this system is a wave vector-dependent notion. You see what I'm saying? This system behaves as if it was two-dimensional at I case. And it's the opposite way of how rotating turbulence does. So actually, that is the essence of the complication, but I was hoping that I could have hand-waved my way through it to make it somewhat plausible. Okay? Now, this is not a proper, the Taylor-Proudman argument is not a proper argument, because by emphasizing the balance between two terms that have nothing to do with nonlinearity, it misses the very essence of turbulence. So that's an argument for low Reynolds number, not for high Reynolds number. The second thing that it does that I dislike particularly is that it obscures the physical origin of what's going on here, which is the nature of the waves that exist in this medium, which you can explore by studying the spectrum of this theory. And in particular, I would like to argue that, in my opinion, at least at a sort of, how to say, a bit impressionistic level, this problem, to a theorist like myself, besides potential application, is interesting because there is a knob, this odd viscosity, that allows you to go continuously from the physics of what people call eddy turbulence to the physics of wave turbulence. I'm going to make that clear momentarily. So first of all, how do we understand the two-dimensionalization properly, mathematically? And again, there was a very, very intriguing talk by Nazarenko a couple of weeks ago, and I'm not going to review everything in there, but here's my version of it. Now, if you want to study these things, less impressionistically, more mathematically, what you would be doing is to write down an equation for how the energy flows. 10 minutes. Yeah, I'll be done. How the energy flows in this system. So you write down the energy, as a function of k. Okay, the same quantity that exhibits the power spectrum. And then you have various terms. You know, you have the energy transfer operator that tells you how the energy is transferred between different wave vectors, and also the forcing and the dissipation. Crucial to the physics of turbulence is the fact that there are strong interactions between the effective degrees of freedom. In particular, if you look at the Fourier modes, the waves, loosely speaking, what you have is that the energy transfer operator depends on products of this velocity fields of their Fourier components, and multiplied by an exponential. And the thing that you have to do typically is to average this quantity. Now, averaging this quantity means that typically that unless the what do you call it here, the stuff that is on top of the exponent, the argument of the exponent, unless the object is 0, the result of that averaging is to make this term vanishing. Now, that object there can be 0 in multiple ways. One way could be a resonant condition. That is a typical mechanism by which you can have that. But the other way you can have this 0 is by having every single entry, omega p, omega q, whatever they're called, omega k, omega p, omega q, all of them equal to 0. Okay? So this is what happens in the odd viscosity. Why? If I take this equation, and as a little exercise, I look at the spectrum of this theory, even neglecting the nonlinearities, I find a spectrum that is omega OK equal magnitude OK times kz. Please notice the anisotropy is still there. And proportionality is the odd viscosity. I'm switching between nu and eta because I just divide by the density. That's just a nomenclature thing. Now, if you look at this, this expression here, notice that if kz is equal to 0, that is to say there is no structure in the z direction, then omega is equal to 0, which means that this two-dimensional manifold of deformation that do not have a z component is going to be able to transfer energy because the average will not be 0. And that's why two-dimensionalization is the mechanism that allows energy transfer. Okay? Now, this argument also shows you how the waves are entering in a subtle way this thing here. And now, what I want to show you is, I think I gave you a plausible, intuitive explanation of that mixed cascade. Now, why don't we do, and here with Xander, trained by Alexandros, and Federico came in with all his muscles. We can just look in this box, okay? And this is the box. So we have, on the left-hand side, there is a normal fluid. The word normal just means odd viscosity equal to 0. And then here there is a odd fluid. The word odd here means take this parameter and crank it up as high as you can, just to contrast the two things. And I don't know how you can see from there in the back, but I would argue that if you look at this picture and you look at this picture, they look differently. Here you can see the beginning. First of all, you can clearly see I would say clearly the anisotropic structure, but you also start seeing the emergence of protopatterns. And the way to do it more properly, of course, is to take a Fourier transform, which is the power spectrum. And if you look at the power spectrum, like here we have normalized the power spectrum of this for different value of odd viscosity, increasing value of odd viscosity, divided by the power spectrum without odd viscosity, you can sort of see that there is a peak. And this peak has a wave vector or a length built in it that is characteristic of the patterns you see. And that length shifts as you increase the odd viscosity. Okay? So what we wanted to do is, well, look, here there is some structure because the peak is broad. There is a systematic displacement. How about we use all this song and dance to do a scaling theory for the behavior of this phenomena. Scaling theory means that we can't solve this model analytically. I mean, with turbulence, I don't feel particularly bad about it. But we want to understand at the scaling level the behavior of this. Okay? So the next slide, and Alexander, this is the second, and then I'm done. It's a touch more technical. is how do you develop a scaling theory of this mixed cascade? So the way we're going to do it is, again, use that logic of separation of scales. When k is small, this is 0, that's Kolmogorov. So Kolmogorov scaling, this we didn't invent it, is that there is a dependence of the power spectrum with a minus 5/3 law. And one way, there are many ways of deriving this result. One way that I particularly like, or I mean I find it inspiring, derived by this gentleman, Krishnan. Krishnan has a formula based on dimensional analysis, I don't have the time to derive it, in which if you insert a time scale, and in the case of Kolmogorov, the time scale is what people in turbulence call eddy turnover time. You imagine is the time scale that it takes for an eddy to disappear, to disintegrate. If you take that eddy turnover time, you stick it in this formula, courtesy of Krishnan, you get Kolmogorov. This we didn't invent it, we just copied. Okay? Now, that is the answer that we're going to get at a small k. Okay? No, large k. No, small k, large distance. Do you see what I mean? But because what interests us is the other limit, not the one that is understood. Because at high k is where odd viscosity is important. So what we're going to do, well, we're going to copy the same formula of Krishnan as a working assumption. But instead of putting for the time scale associated with the eddy turnover time, the lifetime of the basic excitation of eddy turbulence, which is the eddy, we're going to put the frequency of the odd waves. You see, we're squeezing sneakily the physics of waves into this machinery. If we do that, we just kzk, we drop the kz just among friends, we put the k squared. By dimensional analysis, we get this formula. This formula gives another power spectrum. This power spectrum holds a very high k, okay, separated. And a crossover between the two happens when the frequency of the wave and the eddy turnover time are equal. Okay, that's a characteristic time scale that at the level of dimensional analysis separates the two asymptotic regimes. So what we can do is we can divide the k-axis by the wave vector such that this formula and this formula are equal. We call it k-odd. And what you find here in this rescaled picture is a small k, where small k means k smaller than this k-odd. Please notice this k-odd is the value that you put in here so that this quantity is equal to that. You can even see it right away. When you rescale all the curves, you find that a small k, there is Kolmogorov, that looks flat because we divided by the Kolmogorov spectrum. And at larger k, there is a power spectrum with k to the 2/3. K of the 2/3 is not k to the -1 because we divided by the Kolmogorov. It's k to the -1 divided by k to the -5/3. So it corroborates that scaling analysis. And by doing a little bit more song and dance, and Alexandros is a bit impatient, we can also legitimately, we can also understand how the peak that forms after k-odd, where the pattern is forming, scales in a power law fashion with the odd viscosity. Okay? So this is the scaling analysis that you would do. But besides all the, I mean, what I like about the scaling analysis is not so much that, you get a 1/3 or a 1/4. I mean, this is the symptom. The thing that is interesting in my mind is that here you put eddy physics, here you put wave physics, and you have this parameter, which is this odd viscosity, that allows to go from one to the other in a smooth algebraic manner. And that I find it quite interesting. Now, before concluding, I would like to say that why I give you an example of this in the context of a fluid with spinning particles. This is by no means the only thing in nature that can display similar phenomena. Hence my desire of presenting the idea first and the potential realization later, even if it's a bit perverse from the perspective of physics experiment. Similar things can happen, for example, in plasma physics. And moreover, the thing that I'm particularly excited is that, you see, here we've been studying, how shall I put it, Navier-Stokes equation. In Navier-Stokes equation, essentially what's going on is it's a combination of vortex splitting and vortex merging. But what you could also imagine is to study cascades that do not involve energy, but mass. Okay? And Kolmogorov was among the pioneers to try to understand that. The idea would be that you don't single out, say, a pattern, but you can single out a characteristic size of a droplet or a debris or a fragment due to an explosion. And in that case, what you will have is something like object splitting and object merging. And if you look at this paper, in the paper, not the preprint, because we added later, we also studied generalization of this idea, or variance of this idea, in the context of mass cascade, okay, whereas mass that is flowing rather than energy. And with that, let me thank you for your attention and take any question you may have.